Okay, so we saw the definition of norm and trace, and this was in preparation to the proof of the proposition, where we want to show that the ring of integers is a lattice in Qn. But I did not define what a lattice is. So, let me today tell you what a lattice is and prove some of its properties. So, let me first begin with the following lemma. So, let G be a finitely generated torsion free abelian group Okay, so, it just means that it is a finitely generated abelian group and it has no torsion, meaning that there is no element, there is no non-zero element x such that n times x is 0 for some positive integer n. So, that is what torsion free abelian group means. Okay, so, let x 1 up to x n be a set of generators of G and assume n is smallest such possible number. So, assume that n is the smallest possible number like this. Okay. So, there exists no integer m less than n such that you can get m generators for G. Then summation a I x I equal to 0 in G for a I in Z implies that all the a i's are 0. So, there is no non-trivial relation between these x i's. Okay. So, this is quite fantastic because you do not expect this sort of result over for modules over rings in general, right. So, you do not expect this sort of result for Z modules. So, what is the extra thing that we are assuming here? The extra thing that we are assuming here is that G is torsion free Z module. Okay. So, this is almost like what we have with fields, right. In fields, if we take the minimal set of generators of a vector space, then that minimal set is linearly independent over the base field, right. So, this is saying something similar, okay, and this is because we do not have any torsion. Okay. So, what we do is, so let us assume to the contrary. So, assume summation a I x I equals 0 for some a i's in Z, right. So, I going from 1 to n. So, assume that there is such a relation, we want to show that all these coefficients are 0. So, amongst such a relation, take one with the following property. So, amongst such relations, take one that minimizes summation mod a I. Right. So, summation mod a I will be some finite quantity for a relation, and so you just sweep through all possible integers which are less than that particular one and find if you get another relation which minimizes this, right. So, it is always possible to do this in finitely many steps, and so we take this particular one. So, now there are multiple cases that can happen. So, if not all a i's are 0, then we have two cases. case 1 is that only one of ai's is non-zero, right. So, not all of them are 0, which means that there is at least one non-zero, and the first case is that there is exactly one that is non-zero, say A1 is non-zero, A2 and all others are 0. Okay. So, what do we have in this case? In this case we have A1 times x1 equals 0. This means that x1 is torsion. But G has no torsion, right, which means that, but G is torsion free. This means that x1 is 0, that contradicts the minimality of n. Okay, so this case cannot happen. So, it cannot happen that there is exactly one non-zero coefficient. So, let us say there are two non-zero coefficients. Okay. So, say A1 is not equal to 0 and A2 is not equal to 0. We can always rearrange things and multiply the generators by -1 to assume the following. So, we may assume that A1 is bigger than or equal to A2, and this is in turn bigger than 0. Okay. And so, in this case what we can do is we can rewrite it in the following way. So, let me just rewrite it in a simpler way as follows. So, I will replace my, so instead of taking the x1 plus x2 and this as the generating set. Okay. So, what happens in this case is the following. So, A1 x1 plus A2 x2 so on up to An xn, I can rewrite this as follows. I can rewrite this as A1 minus A2 plus A2 times x1 plus x2 so on up to An xn. Okay. And so, now you notice that, sorry, I have forgotten an x1 here. So, you notice that x1, x1 plus x2, x3 and so on xn is also a set of generators of G, and in this case what are the coefficients? Well, it is A1 minus A2, A2, A3 and so on, and if you take the sum of these, summation A1 minus A2, sorry, maybe it is not a good idea to write it as a summation, but if I just take this, then what do I have? Then I have A2 plus mod A3 and so on up to mod An, right. But I know that A1 minus A2 is positive and A2 is also positive. So, this is same as A1 minus A2 plus A2 plus mod A3 so on up to mod An, which is just A1 plus A3 and so on plus An, which is strictly less than well, I do not need to put mod, but which is strictly less than A1 plus A2 plus mod A3 and so on up to mod An. But this contradicts the choice of my coefficients, contradicts minimality of summation mod Ai, right. And so, this case cannot happen either, right. So, hence summation Ai xi equal to 0 implies that Ai equal to 0 for all I. Okay, so that's something about lattices. So, a minimal base, let G be a torsion free, a finitely generated torsion free abelian group a minimal basis of G is a generating set with as few elements as possible, right. So, that is what a minimal basis is, and it makes sense. Okay. So, now next thing I am going to prove a lemma, but I am simply going to sketch a proof of this. I am not going to give you all the details. It is essentially what is called the structure theorem for finitely generated abelian groups, and you should have seen this in your abstract algebra course, but this is a slightly different way of presenting it than what is usually done, and I like it. So, I am going to sketch it here. Usually it is done in terms of matrices, n by n matrices over or m by n matrices over integers using row reduction and column reduction, etc. This is essentially the same thing, but we are going to do it abstractly with finitely generated torsion free abelian groups. Okay. All right. So, let G be a finitely generated torsion free abelian group. Let H be a subgroup of G. Okay. So, in particular H automatically becomes torsion free and it is also finitely generated because Z is Noetherian in any case. So, there exists a minimal basis x1 up to xn of G and integers m1 up to mr. Okay. So, here r is going to be the number of generators in a minimal set of H. Okay. So, that is why there is n here and r here, it is not a typo. For r less than or equal to n, such that the following two things happen. So, one is that mi's are all bigger than or equal to 0, mi divides mi plus 1 for all 1 less than or equal to I less than or equal to r minus 1. So, this you may see some resemblance with the structure theorem of finitely generated abelian groups, and this mixi for I between 1 and r is a minimal basis for H. Okay. So, further, if the index of H in G is finite, then R is equal to n, right. So, we saw that, we saw that R is less than or equal to n, saw in the statement, we have to prove it, r is less than or equal to n. I am saying that actually r is equal to n only in the case when the index of h in G is finite. Okay. All right. So, how do we prove this? So, this is a bit of a complicated induction as you would expect, right. We are trying to do some row and column reduction, and so from m by n you go to 1 less, right, m minus n by n minus m minus 1 by n minus 1. So, you are going to do something similar. Okay. So, so the choices are a bit sort of awkward and complicated. So, let me try to do this carefully, but a lot of checking I will leave to you. So, let H be an element in H such that, so I will first choose a good element in H if H is summation A I y I, okay, I going from 1 to n. So, yeah, let me tell you what how I choose this. So, I am not actually working with my minimal basis given minimal basis. I am saying that I take some other minimal, possibly some other minimal basis yi, and I want to write my elements of H in terms of those bases, but there is a reason for this, and the reason is that GCD of these AIs, so A1 up to AN is smallest possible. Okay. So, what am I doing? I am just yeah. Right. So, what I am doing is I am choosing a minimal basis of G y1 up to yn, and then I am writing all possible elements of H in terms of this basis, and then I am choosing an H with the such that the GCD of the coefficient is the smallest possible one. Okay. All right. Now, once I have done that, I can change my integral basis, I can change my minimal basis, because what happens when you change basis of a Z module, you are essentially you are multiplying it by a unimodular matrix in Z. So, a matrix over Z with determinant 1 or minus 1, right, because those are the only units in Z. So, you do not change the GCD of the coefficients, you will change the coefficients, but not their GCD. Okay. So, now amongst the, so once you fix such H, sorry, once you fix such Y, so you choose basis y1 up to yn such that summation mod ai is smallest possible. Right. So, you can also do that, because once you have fixed one basis, there are only finitely many things to check, and so you can get this as well. Okay. So, first you minimize the GCD, then you minimize summation mod AI, right, and we are going to use the trick that we used in the previous lemma again. All right. So, here is the sketchy part. So, as before, we show that only one of AIs is non-zero. Okay. If two or more are non-zero, we are going to rewrite it so that summation mod AI becomes a smaller for a different choice of basis. Okay. So, say without loss of generality, I say that A1, which I will also decree to be M1, is not 0. Okay. So, M1 is now, my M1 is fixed. All right. Also observe that GCD of A1 and 0 0 0, this is same as A1, right, and I also assume that this is bigger than 0, which is also M1, right. M1 is my A1, all right. So, this gives me, I have to construct a integral basis and all these integers mi's, but so this is how I have done it. So, what is H? H is just M1 times Y1 and this is in capital H. So, this is my one of the good nicely chosen element of H. Okay. So, now let Z be an arbitrary element of H, right, and I can always write that in terms of an integral basis of G. So, Z be an arbitrary element. So, here are a bunch of exercises that I am going to give. I want you to show that M1 divides B1 first, right. If not, you can always find things with a smaller GCD. Okay, so that's the idea. Then exercise 2. So, these are all very easy exercises that you just have to write down, manipulate things and write down. So, so we know that Z is in H, but that does not necessarily mean that Z minus B1 Y1 is in H, but the second exercise tells you that actually this is the case. So, B2 Y2 and so on up to B n y, this should be Y2 Y n, this is also in H. Okay. So, this again is just about writing it down in terms of Z and a multiple of H. So, that is easy. And then exercise 3 is the following, it is that M1 divides Bi for all I bigger than or equal to 2. Okay. All right. So, the upshot of all this, so now we have completed our sort of row and column reduction to get one row which consists of all zeros and another row which consists of all column which consists of all zeros. So, what you can do is then the third part. So, another exercise if you like is I just take the subgroup of G generated by Y2 up to Yn and then the subgroup of H which is just G1 intersected with H. Right. So, this is a subgroup of H, and so the last exercise, well maybe not the last, but the last major exercise is to show that G is actually a direct sum like this, an internal direct sum, and H is an internal direct sum like this. Okay. So, we have finished our row and column reduction to get it this way, and now you use induction on number of generators. Number of generators of G, right. So, you have replaced G by G1 which has one fewer generators. So, you can redo the game and do this. Okay. So, that proves this. So, now we are ready to define what a lattice is. So, proposition. So, V is either Q to the n or R to the n, and K is either Q or R depending on which situation I am in. So, either I am considering a Q vector space or an R vector space. Okay. So, a lattice, so this is proposition slash definition. A lattice lambda in V is a Z module contained in V satisfying any two of the following properties. following 3 properties. So, this is the definition part. So, what are the 3 properties? Lambda spans V as a k vector space. 2, lambda is discrete in V. So, V is either q to the n or r to the n. So, V comes with a topology, and in this topology lambda is discrete. So, what does, sorry, this is it looks like it is lambda to the 3, but this is sort of 3 like this. So, what does it mean? It means that lambda is a discrete subspace in this topology. It means that you can around any point in lambda you can find a neighborhood which does not contain any other point of lambda, and because lambda is a Z module, it is a group in particular, you just have to check around 0, right. So, 0 is in lambda and you have to find a neighborhood of 0 which does not contain any other point of lambda, okay. And lambda is a free Z module of rank n, okay. So, this is the definition of what lattice means, but then the proposition is that any 2 of these properties implies the third. Okay, so that is the definition, and what I am going to do is I am going to prove for you that 2 plus 1 plus 2 implies 3, and other things will be exercised. So, you also have to prove that 2 plus 3 implies 1 and 1 plus 3 implies 2, but those are easy exercises. Okay, so, exercise 1 plus 1 plus 3 implies 2 and 2 plus 3 implies 1. So, these are exercises. We prove that 1 plus 2 implies 3. Okay. So, what is 1 and 2? Well, 1 is that lambda spans k and lambda is a discrete subspace of V. Okay. All right. So, how do I prove this? All right. So, let me get straight to it. So, what I do is, so as lambda spans V, there exists a basis of V contained in lambda. Okay, so say x1 up to xn, and you define lambda 0 to be zx1 plus zxn. So, this is a submodule of lambda, right? It is a submodule of lambda. So, I have already now used the first property, now I want to use the second property, right. So, lambda is discrete in V, which means that there exist m bigger than 0 such that if summation lambda I x I belongs to V I between 1 and n, and lambda I, so mod of lambda I is less than m inverse, then this element x, then x is not in lambda, right, in lambda minus 0. So, x could possibly be 0, that is okay, nothing else is in there, right. So, that is what it means. So, what I can do is I can So, this part will be a little bit sketchy. We can divide the cube of length 1 into m to the n different parts. So, I am assuming that m is just an integer, right. So, m to the n parts, each of length 1 by m. So, you take the standard 1 cube near the origin and you can divide it into m to the n parts. So, you are dividing each of its side into n parts of length 1 by m, and then you are taking all the cubes like that. So, what this means is that if x in lambda minus 0 is x equal to summation lambda not lambda, I do not know what I want to say here, yeah, ai xi, then we can divide, we can sort of subtract x prime in lambda 0 such that x minus x prime is summation ai prime xi with ai prime mod of this less than 1. Okay. So, this shows that lambda 0, I do not know how I denoted it, lambda sub 0 I think, yeah, lambda sub 0 has finite index in lambda. Okay. But now we know that lambda is a finitely generated torsion free abelian group, right. So, lambda is a, and lambda 0 is a finitely generated torsion abelian group of rank n. So, by previous proposition, lambda 0 is a finitely generated torsion free abelian group of rank n. So, that proves our 3, right. Okay. So, so we are out of time. So, what we did today was mostly look at properties of finitely generated torsion free abelian groups, and we proved, we essentially proved structure theorem for finitely generated abelian groups, but it is just a slightly different perspective on it. It is a more abstract algebraic perspective on it. So, that is why I gave it to you, but you can very well use structure theorem for finitely generated abelian groups to prove this last proposition that we had. And so, in the next class we will use this the thing that we studied about norms and traces, and the things that we studied about lattices to prove that OK is a lattice in Q to the n, okay, and then we will take it on from there.